Hello, welcome back. The title of this lesson is called Free Body Diagrams. This is part one. Truly one of the most important lessons in all of physics, especially in mechanics, the motion of objects in physics, because a first step that we always take every time we solve a problem in physics where something is moving or there are forces acting on an object is we first have to draw a picture of just the object in isolation by itself and then write down using arrows all of the forces acting on the object. Because remember, Newton's second law states that the sum of the forces acting on an object when we add them up using vectors is equal to the mass times the acceleration. So it tells us how something starts to move when we know the forces acting on the object. So the only way we can start a problem is by drawing a picture of the object and drawing all the forces acting on the object. So we have to simplify the diagram into what we call a free body diagram that shows every force acting on the object. All right, so that's the wordy way of telling you what we're doing. So let's first consider, not a real problem, but let's just consider a box sitting on a tabletop. And let's see if we can write down probably the simplest free body diagram I can think of. So let's say, or I guess I shouldn't say it's probably the simplest, but it's one of the simplest free body diagrams we could think of. So here is a table, a very nice solid oak table, right? And we have an object sitting on the table. So you would start, like if your problem said, hey, there's a box on a table, the mass of the box is m kilograms, right? Then you label it, or if it's 5 kilograms, you put 5 kilograms there, sitting on a tabletop, and then some stuff is happening to this box. But in this case, the box is stationary, and so it's not moving. Okay, so we know, because we know Newton's law applies to any object. So we know that the sum of the forces that are applied to an object is equal to the object's mass times whatever acceleration the object actually has. But this box is sitting on this tabletop and it's not moving. You look around the room and most of the things in the room are not moving. So therefore we know, without doing any fancy physics, that the forces, when we look at all the forces that are acting on all of these objects that are stationary in the room, the forces have to add up to 0. If the forces that were applied to all of the objects around you, if they were unbalanced, where we had a non-zero net force, then the object would move. Because forces on an object, when you have some non-zero force, when you add them all up, it's going to produce an acceleration. Always, right? So all of the stationary objects, if you had to look at invisible glasses you could put on and look at them all and see the arrows, the vector arrows of the forces, you would have to see a situation where there's no net force acting on all of these objects. So what we have to do is draw a picture of the crate, the box, whatever it is, in isolation by itself. That's why we call it a free body diagram. If we're trying to study how this box moves in physics, then the table truly doesn't matter at all. The air circulating around doesn't matter at all. The planet Earth, which is down here, doesn't matter at all. Mars is over here, Jupiter's over here. We have another star system 5 light years away over there. None of that stuff matters. All we care about is the box. So in a free body diagram, whatever it is you're trying to study that might be moving, or if it's just some object that you're studying in equilibrium where it's not moving, that is the object that's the center, the main event of the free body diagram. So what you do is you take this as your initial, your sketch of what's happening, and you translate it into a situation where only the box is in isolation by itself. We remove the table, we remove the planet Earth, which I didn't draw to begin with, but we forget about it, forget about the stars, forget about the planets, forget about the air, forget about everything else. All we want to do is write down the forces that are acting on this box. So then you start thinking about what forces are acting on this box. The very first force that you know or think about may be acting on this box is the weight of the box. You know that the Earth is down here. We haven't drawn it because we don't care about it, but we know the Earth is exerting some force on here. We call it the weight. So what you do is you draw an arrow down, which represents the force going down, and you can put W for the weight, but we know that the weight is equal to mass times the gravitational acceleration. So whatever the mass of this box is, multiplied by 9.8 if we're talking about Earth gravity, is going to be a force in newtons, which is acting downward, and it's acting on the box. All right? Now, here's where I have to talk a little bit. As we get going with free body diagrams, it's going to be fast. I want you to get into the habit of drawing these things quickly, because you can't spend 10 minutes on a problem goofing around making a beautiful drawing. You have to get quick, right? You have to get fast. But in the beginning, we have to talk a little bit because there's a lot of stuff going on. You see, we already learned from Newton's third law of motion that for every action is an equal and opposite reaction force. But those forces, the action and the reaction forces, they do not act on the same object. They always act on the partner object there. So for instance, when this box is sitting on the table, we know there's a force due to gravity. That's the force of the Earth acting on the box. But there's a partner force, a reaction force, where the box is pulling up on the Earth. So those two forces, one of them's acting on the box and one of them's acting on the Earth. They do not act on the same object. So in our free body diagram, we don't draw any forces that were acting on the Earth because we only care about the forces acting on the box. So that's why we don't have any of those reaction forces, in this case acting on the Earth, there. Now also, this box has a weight which is acting down. That is a force on the box. But because the box is sitting on a table, that force, which is the weight, is transmitting that force into the contact here between the surfaces, and then there's a force on the tabletop. But see, that is a force on the table. And we don't draw forces on the table for the free body diagram for the box because we only care about the forces acting on the box. So it's a little bit of a subtlety. This pen, I have a force of gravity acting on it from the Earth, but when this pen is sitting on this paper, so we have a force of gravity of the Earth acting on the pen, but then the pen in turn acts and transmits the force into the paper. But again, we don't draw that force either because that's a force on the paper. The paper is not the object of interest. But what happens is, because this thing is transmitting a force into the paper, there's a reaction force which we call the normal force of the paper acting on the pen. In this case, we have this box acting on the table, and the table is then pushing up on the box. That would be a force acting on the box. So there's actually an upward force here, right, which we're going to call the normal force. I'll put F sub n, or you might even just label it N for the normal force. These are the two forces acting on this box in this situation. There are other forces around that are related to what's going on. Let's go through them one more time again. The Earth is pulling on the box. The box is pulling on the Earth. That's an action and reaction pair. This box is pushing on the tabletop. That's acting on the table. And the table is in turn acting on the box. So you see how I've just labeled 4 forces, but only 2 of them are actually acting on the box, because one of the forces was acting on the Earth and one of the forces was acting on the table. For the free body diagram, we don't draw any of those forces. We only draw the forces acting on the box. And the forces acting on this box is the Earth pulling down on the box due to gravity and the table pushing up on the box, which we call the normal force. Okay, now we're not going to turn this into a full-blown problem, but let's ask ourselves a question. We don't believe there are any additional forces acting on this thing. We don't think there's any additional forces. We think this is it. And this box is not moving at all. Therefore, since F equals ma for any object in the universe, and if it's not moving and not accelerating, then acceleration is 0, then that means, since the mass of the box is non-zero, it's just a number, that means that the sum of the forces acting on this box has to be 0 because it's not moving, it's not accelerating. Okay? So is that the case here? We have a situation where we have a downward force acting on the box and an upward force acting on the box. And because we know the box is not accelerating, it's completely motionless with the acceleration 0, we know without doing any math that this upward force, the normal force acting on the box, is exactly equal to the weight of the box. And so those forces are exactly equal and opposite, and they cancel, which means they add to 0. And so basically, when you look at this situation, there is no net force acting on this box, and that is why the acceleration of the box is 0. If I walk over to the box, literally if I walk over with my hand and I pull up on it, then suddenly I increase the force in the upward direction because I grab it, and then I make an unbalanced situation where the upward force would be bigger than the downward force, and therefore the net force would be up. So the box would accelerate up. I would be lifting it up off of the table. But when everything is balanced, everything around you, look around the room. If you could see those arrows, there would be weights going down and normal forces going up. Now, I need to talk a little bit before we do a little bit more work. When we talked about in Newton's third law, we said action and reaction forces never cancel. I even wrote it down 6 times. They don't cancel, they don't cancel, they don't cancel. And here, I'm telling you that these two forces cancel. So what's going on? Well, it's a subtlety, okay? It's a subtlety because these two forces are actually not an action-reaction pair. I'm going to say that again. These two forces are really not an action-reaction pair. I'm going to say that a third time. Those two forces on the board are actually not an action-reaction pair because what's actually happening is the Earth pulls on the box. The box then pushes on the table, and the table reacts and pushes on the box. So the Earth acting on the box is a force, and the table acting on the box is a force, but you see there was an extra step in there. There's really four forces involved, and these two on the board, those are just forces acting on the box. The Earth pulling down and the table pushing up. Those are not technically action-reaction forces. The reaction-reaction forces I've listed 3 or 4 times by now verbally, so you should know that even though you think they're the same ones maybe that are on the board here, they're really not. These are two forces acting on the box. All right? And then the next thing I need to talk about before we jump and do the rest of our problems is that in equilibrium, the forces will be balanced, giving you a net zero force, which means the thing doesn't move. But then, of course, if I take the table away, for instance, let's just talk about it. What would happen if I took the table away? If I remove the table, then there is no more normal force. This force is gone. The only force acting on that thing would then be the weight. And then, of course, we'd have an unbalanced set of forces. We'd have a force acting downward, which would produce an acceleration going downward. The last thing I'll say about this before we draw the rest of our free body diagrams is that in your free body diagrams, you should never, ever, ever draw on a single free body diagram an action-reaction pair. Why is that? Because a free body diagram is just the object of interest. And an action-reaction pair, we already said 16 times, they act on different objects. Earth pulling on my marker, marker pulling on the Earth, acting on different objects. If I'm flapping my wings, my hand is pushing on the air, and then the air is pushing on my hand. They act on different things. So because action-reaction pairs act on different objects, they can never appear in the same free body diagram. All right, now let's jump ahead and do something a little more complex than this one, and we'll just kind of take it one step at a time. Draw a free body diagram for the following situation. A box is dragged across the floor at a constant velocity. The box is being pulled by a rope horizontally, and there is opposition to the forward pulling force by what we call friction. Now, we're going to talk a lot more about friction a little bit later, but you all know what friction is. It's that resistance force as you drag things across a surface, okay? Or, you know, even when you rub your hands together. That's what friction is. We're going to talk about a lot more about friction later. So we have a more complex situation. So first, let's draw an initial drawing that will not totally be a free body diagram, and then we will go from there. So what we have is some box, and you can draw the ground if you want to, right? Now in a free body diagram, we would never draw the ground. We only want to draw, for the free body diagram, the box. But for right now, we're going to leave it there because we're just doing our initial sketch. All right? And then we have, you know, some person here. You can draw that if you like. You don't have to. And basically, there is a rope connected here. And basically, he or she is pulling with some force, which we call F sub P because it's a pulling force. F sub P, pulling on a rope. So you could draw a rope if you want, or you can just draw an arrow there, okay? Now, there is an oppositional force to this because you know that if you pull something this way, there's going to be a tendency for a resistance force of friction to pull in the opposite way. And so where is the frictional force going to be? Well, it's somewhere here at the bottom because the frictional force is happening due to the interaction with the ground. So you could draw a little arrow like very close to the ground down here to represent friction, and you could call that F sub lowercase f, which is the frictional force. And I've drawn the frictional force in the opposite direction, still in the horizontal direction, but in the opposite way of the pulling force. The frictional force cannot be in the same direction as the pulling force, otherwise it would accelerate it, and that is not going to happen. It has to be in opposition to the pulling force. Now, what other forces do we have on this thing? That we need to consider. Well, this object has some sort of mass, and because it has some sort of mass, it has a weight, which we call mass times gravity. Weight is equal to mass times gravity, and that acts downward. And that's a force of acting on the block. And then the block, of course, is transmitting that force into the contact force of the ground, and the ground is then pushing up with a normal force, and then we can say that there's a normal force going up right here. But both of these forces, we can talk through it one more time as we did just a minute ago, just to make sure you understand what's happening is the Earth is pulling down on the block. The reaction force to that is the block is pulling up on the Earth. We don't draw the Earth and don't care about that, but we can still leave this one in play. Because this is acting on the block, it's pushing onto the ground, and the ground's reaction force is pushing up as a normal force. And again, if you get confused or you don't know where this normal force comes from, it comes from any physical surface. When you place an object on it, it's going to tend to microscopically deform the surface. And the chemical bonds that are in there between the atoms and the molecules they behave like little rubber bands, and as you stretch it, it wants to pull back. So as you deform it, it wants to spring back. Springing back is what causes the normal force. You don't know how big they are, but you know there's some force up and there's some force down. Now, what we need to do is try our best to draw a free body diagram of this situation. Right? Now, it says that a box is dragged across the floor at constant velocity. So it's not accelerating. Constant velocity means acceleration is 0. So we know that any object, the sum of the forces acting on any object is equal to the mass times the acceleration. So they don't tell you this in the problem. The way they phrase it, we rephrase it is, it's pulled across the floor at a constant velocity. That means like 1 meter per second constant velocity, or 5 meters per second constant velocity, or whatever. But it's not speeding up and it's not slowing down, and that means there's no acceleration right here. So if we were to take a look at this situation and draw a more proper free body diagram, what we would do is this. Now that we kind of have our general idea here, we remove the ground, we remove the person, and we draw a simpler diagram with just the box in free space, because that's what we really care about. And we know we disregard the people, the planets, all that stuff, and acting on this box must be a force in this direction, which is a pulling force. And we did draw this other force near the ground, but for a free body diagram, we don't have to do that. We just draw a left-hand force right here, which is a force due to friction in the opposite direction. And then we have a force acting down, which is the force of gravity, mass times gravity of the object, which is the weight of the object. And we have some force acting up here, which is called the normal force there. So there are 4 forces acting on this box. And if all of these arrows are equal and opposite to each other, then you can see that there's not going to be any net force on the box if they're all in balance. So let's see what Newton's law tells us should happen here. The sum of the forces is equal to mass times acceleration. So we don't look at this diagram. Let's look at the more simple free body diagram right here. So let's take a look in the x direction. We always look in the x direction and the y direction first. So what we say is the sum of the forces in the x direction is equal to the mass times the acceleration there. So the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. But what are the forces in the x direction? Well, what you do is you consider anything pointing to the right being positive and anything pointing to the left being negative. So Fp is a positive number, and Ff is a negative force. And because this is positive and you add it to this, which is negative, you can just write it as a subtraction F sub F here, like this. All right? And so when you put these guys in place, this is the positive force to the right, this is a negative force to the left, and what you're basically saying is it's equal to the mass times what is the acceleration? It says the box is moving with constant velocity. That means it's not accelerating, and so the acceleration is 0. So Fp minus Ff, the frictional force, is equal to 0. And so because it's equal to 0, I can move this to the other side, and I can say that I know that the pulling force is equal to the frictional force. I can kind of circle that if I want to. So now we've proven mathematically that this arrow pointed to the right has to be exactly the same length and strength as the frictional force pulling to the left. Because if it wasn't that way, then the thing would be accelerating. If I was pulling harder on the left, like really, really, really hard, and unbalancing this situation, then I would be overcoming the friction. I would have a net force to the right, and since force is equal to mass times acceleration, the box would be accelerating, speeding up. But what is happening in this case is I get it going, and once I get it going, it's like just kind of like walking with that, with that thing tied to your waist. and you're still pulling and there's still a frictional force, but because everything's balanced, you're just moving at a constant velocity. You're not accelerating because you're still pulling, that's still happening, but the dragging is canceling it out in such a way you're still moving at a forward velocity, but you're not accelerating. Because remember, once things start moving, they always tend to move forever and ever unless acted upon by an outside net force. So once you get the box moving, if there's no net forces acting on it anymore, it's going to keep moving. So it's moving at a constant velocity. All right, so then let's take a look in the y direction. And we're going to do the same thing. We're going to say the sum of the forces in the y direction is the mass times the acceleration that exists in the y direction. But what are the forces in the y direction? Well, we consider positive y to be up, so we have a normal force. And then downward, we have mass times gravity. That's going to be opposite, which means it's negative, and so it's going to be like subtracting mass times gravity is equal to the mass of the object times the acceleration in the y direction. This thing is sitting on the ground. It certainly is not accelerating up or down, so again, the acceleration is 0. So n minus mg is equal to 0 on the right, and we move this to the other. The normal force is equal to the mass times the gravity. What we have figured out is that the normal force acting on the box from the ground is exactly equal to the weight of the box. Now, these are not action-reaction forces, okay? So that's the thing that gets students very confused. It appears that they are because some of the numbers are the same value. But what's happening is Earth is pulling down on this. The reaction force to that is this thing pulling up on Earth. We don't put that in the diagram. Because it's sitting there, it's also pushing on the tabletop, and then the tabletop is pushing up on it. So the two forces acting on the box in the up-down direction is weight acting down and the table pushing up. And these are not action-reaction. I've listed their action-reaction forces, which act on different objects. These are two forces acting on the block, but we know they have to be the same because mathematically we've said the normal force has to be equal to the weight in order to keep this balanced because this box is not moving up or down. So this is a long-winded way of saying that this situation, we have two forces acting in the vertical direction, two forces acting in the horizontal direction. If the box were still, it would be exactly like stationary. It would be the same situation as here. We would have the pulling force equal to the frictional force, but the thing may not have started moving yet, okay? You know how when something really heavy is on the ground, you can start pulling on it, but it doesn't move yet. There's a resistance to your pull called a frictional force. Once it starts sliding, then there is still a frictional force after it is sliding, fighting your pulling force. In this case, since it's moving at a constant velocity, the pulling force is exactly equal to the frictional force, nullifying the force in this direction, but the thing is still moving because an object in motion tends to stay in motion. When something starts moving, it keeps moving. And there's a zero net force in that direction, so it's going to keep moving at a constant velocity. And similar thing in the vertical direction. The up and the down force is balanced because the thing is sitting on the ground. Now, my goal over the next several lessons is to draw a lot of free body diagrams, but do a little bit less talking for every one of them. I have to talk a lot in the beginning because it's very easy to gloss over it, and then you think some of these things are action-reaction forces, but they're not. Action-reaction pairs should never appear in the same diagram. When you are looking at a box or a football or a baseball or a spaceship and that's the object of interest, you're only drawing the forces acting on that object. And any reaction forces are acting on some other object. You don't draw those, but you have to write down every force acting on the object. And then we apply Newton's law in the horizontal direction and Newton's law in the vertical direction, and that is going to tell us how the thing what accelerations are acting on it. And we're going to get a lot of practice moving forward. So I'd like you to watch this a couple of times. Follow me on to the next lesson. We'll get more practice with free body diagrams.